开始 record。已经开始 record。啊。藏起来。这个是，Hello。点右边小键。这个。Hello。Hello。刚刚还行啊。连接不稳定。有点僵硬。哎。但是这儿好像没有显示我的声音，好像很小。Can you hear me？ 好像是可以。Okay. And can you see the screen? All right. So let's just start. So good evening, everyone. I'm very glad to be the first speaker of this series of seminar. And today I will give a very general introduction to topological order. So I think it will be quite friendly this time, since there won't be like a complicated mathematical calculation. I will just tell you like the history, like the development of the topological order, and I'll tell you the motivations, like why it's important and why we're interested in. And so that's the first part. All right. So the second part, like I will give you some little bit more precise definition and notations of topological order. So let's get started. So I want to begin with the most fundamental and important questions in condensed matter physics. So what is a phase of phase transition? So for a simple example, like at a constant temperature P, okay, and at a constant pressure P. So there is a like transition temperature T0. So below this temperature, so it will be the ice phase, right? And above this temperature, maybe below some other liquid and gas transition temperature, like T1. So this will be the water phase. So no matter the where the exact temperature you are in, as long as the temperature is below this T0, it's ice phase, and as long as it's above this T0 and less than T1, you have a water phase. So roughly speaking, a phase is just an equivalent class of states of matter. But it's very hard to give a very rigorous definition of this equivalent class. So if we have defined such equivalent class, then we define a phase, and a phase transition is just a transition between different equivalent classes of states of matter. So so let's just let me give you a rough description of such equivalent class. So you can just think that in the space of states of matter. So so if two states of matter if they are connected by a test, and then all the physical properties are continuous along this test. and the physical properties. How long is this? Then we say these two states of matter are equivalent. So equivalent. And then if along this path there is some discontinuity, so there is a phase transition. So by continuous, I mean that like the thermodynamic, just for example, the thermodynamic observable like the energy or the heat capacity, something like that, are some continuous function as a function of like some parameter, like temperature or some external field. And also like if the system is gap, and then the gap is there is no gap closing along this path. And if the system is gapless, then there is just no gap opening along this path. So we see this is what we call the physical properties are continuous. So based on the idea of this continuity or discontinuity, so actually a phase transition can only happen in the thermodynamic limit. So based on what we have talked about a phase transition. Only thermal So this thermodynamic limit just means like the spatial size of the system goes to infinity. Okay, but you need to keep the intense quantity, like the temperature or the pressure a constant, and you let the size of the system go to infinity. So that's what I mean by thermodynamic limit. So an argument of this statement is that the partition function, okay, is a continuous function. Like it's a function of the form like e to the beta h, right? And then your correlation function or some other thermodynamic quantities can be derived from this continuous function. So if the system is just finite and the quantities you get is always continuous, okay? Only when you take the thermodynamic limit, there will be the discontinuity will occur. So I think it's just like the Fourier transformation. The cosine function and sine function are some continuous function, and as long as so only when you add the infinite number of this cosine function or sine function, you will get some discontinuous function, right? Like the square wave, right? You can so it's a superposition of the infinite number of continuous sine function and cosine function. So let me give you an example. So let's talk about the one-dimensional transverse Ising model. Okay, the Hamiltonian of this model is if you have any questions, just interrupt me. Okay, this is a Hamiltonian, and so we want to find the ground state of such Hamiltonian, and actually, it's this model is exactly solvable. Okay, by some it's a little bit tricky, but it's exactly solvable. So we can just take the limiter like if g goes to infinity, or so the first term is not that important, right? And so the ground state of such of such Hamiltonian will be just all spin pointing right. Right. Oh, sorry, pointing up. And if this g is much smaller than 1, so the second term is not that important. And the ground state is all spin pointing right or pointing left. Right? It's just a Ising interaction. So it seems there is some phase transition in between, and it actually is. So at g is equal to 1, there is a phase transition. So as I just said, this model is exactly solvable. Okay. So its ground state just behave like this. So this Hamiltonian can actually be divided into 2 sectors according to some other quantum number. And we can find the ground state of each sector. Okay, so there will be 2 states which have the lowest energy. So I will draw the picture that these 2 states with lowest energy. So I will show their energy difference. Like so for one state, I call it psi A, and another is psi P. So EA minus EP, and as a function of T. So if the lattice size is small, like it will be something like this. So this is the number of lattice size is equal to 2. Okay, it's a continuous function. And if we increase the number of lattice size, so the function will just something like this. This is the lattice size is equal to 8. And if we just increase the number of lattice size, so the energy difference will 0. So just it's almost 0, and then goes up. And here is g is equal to 1. maybe L equal to 16. So if the number of lattice sites is small, like they're just 2 sites or 8 sites, there is no continuity. But if the number of lattice sites is large enough, there will be some discontinuity. And then I will draw a picture of their spectrum. Yeah. So this site A is the exactly ground state, and this is the the first exciting state. So the picture will like this. I will like the L is equal to 16. So it will be something like this. At G is equal to 1. So when G is smaller than 1, there will be 2 states which are almost degenerate. Okay, just this psi A and psi P. Almost degenerate. And then when G is bigger than 1, the degeneracy will split. Something like this. And the other excitation states is something like this. Okay. And if we really let this number of lattice sites go to infinity, so so this state will exactly touch the energy of these 2 states. So at the thermodynamic limit and at G is equal to 1, so the system is gapless, exactly gapless. And so if G in the thermodynamic limit, so if G is less than 1, so it's a gapped phase. And with 2 almost degenerate ground states, and G is equal to 1, it's gapless. And if G is bigger than 1, it's again gap. But this gap is some kind of trivial since there is no ground state degeneracy. So degeneracy just splits. Okay. However, so in the thermodynamic limit, we can see exactly there is some phase transition like this. But if you do not take the thermodynamic limit, so at G is equal to 1, there is just no discontinuity. So the phase itself is not that well defined. Okay, and the state at G is equal to 1 is not gapless. So I just want to emphasize that a phase or phase transition is only well defined at the thermodynamic limit. Okay. So the theory of phase transition, is Landau-Ginzburg phase transition theory, and it was proposed at around 1950. Okay, and the basic idea of this theory is that a phase can be described by some order parameter, some parameter called order parameter. So bundle series a face. And usually the system will have some symmetry, okay, described by a symmetry group G. And if there is a phase transition happening, the symmetry of the system or the symmetry of this order parameter will be described by another group, which is a subgroup of G. So so here I just mean that a symmetry operation or a symmetry transformation acting on this order parameter is invariant. Okay, but like if there is this transition, the symmetry is so-called simultaneously broken. So after the phase transition, the symmetry will become some subgroup H of G, which means that at this phase, so after phase transition, so if you have a phase A and a transition to phase B, so the order parameter in this phase is not invariant under the G group, but it's still invariant under this H group. So the phase is so symmetry is just simultaneously broken. So an example, good example is like the classical 2D asymptote. Because which means the nearest neighbor interaction. So there are two phases of this Hamiltonian. Like if the temperature is bigger than some critical temperature, so the average value of the magnetic moment is just a 0. Okay, so if T is less than Tc, and yeah, this system has a global Z2 symmetry, which means that if you just take the Z2 transformation, like sigma I Z2 minus sigma I Z, the Hamiltonian is invariant, so it has this global Z2 symmetry. And if we so at the this phase, so the average magnetic moment is 0. So if we like act this symmetry transformation, this phase, so this parameter is invariant, right? -0 is still 0, so it's invariant. And if t is smaller than t, say, there is some constant average value of magnetic moment. This is m, which is not 0. And then, if you make such symmetry transformation, so -m is not m anymore. So there is a simultaneously symmetry break.
May I have a question?
Yeah.
Yeah. When t is smaller than t, the Z2 symmetry is still there. So why there is a non-zero magnetic moment? I guess this is the square of the sigma.
Sorry.
Square of the sigma.
I mean this.
Yeah. Because Z2 symmetry is still
Actually, when I mean this under this correlation function, you cannot just take the like trees sigma I e to the right. So if you just calculate this, it's always 0, since there is always a Z2 symmetry, right? So what we actually do is you need to add infinitely small external field, and then this external field goes to 0, and we will get a non-vanishing. Yeah.
You mentioned that when you have a phase transition, you will, instead of the original G group, you will have a subgroup.
Yeah.
And in this
So
case,
this subgroup is just a trivial group, identity and trivial group. Okay. So actually, the symmetry breaking theory or Landau theory, so it's very it works very well in the classical phase transition, but for the quantum phase transition, like where we have talked about the quantum, the transverse field quantumizing phase transition, it's a little bit tricky, but intuitively it's right. So there are some subtleties, but intuitively it's right. And this symmetry breaking theory is very general, which means that no matter what type of interactions your system have, you can have column interaction or spin interaction or whatever, as long as they have a same symmetry and breaks into the same subgroup. So the properties near the phase transition are the same. Like for example, how to say this? So the physical properties near the phase transition can, in this case, it can always be expressed like T minus Tc of some power. Okay, so as long as they have the same symmetry, and they breaks into the same symmetry, so this power called the critical exponent are the same. Okay. So the symmetry breaking theory is very general and very universal. So far, physicists just thought that they have enough knowledge to understand all kinds of phase transition, as long as I know the symmetry. And so after the symmetry breaking, So it breaks into what symmetry. So it can be understood. However, at around 1980s, a special kind of so-called quantum gapped quantum liquid phase was discovered. So in this kind of phase, so different phases have exactly the same symmetry, but there is this transition. So the Landau paradigm is no longer useful anymore. Okay, so there are three main sources of this discovery. The first is fractional quantum Hall effect. So a new type of gas. We have not defined what do we mean by gap quantum liquid, but we'll talk about it later. It's discovered. So it's beyond Landau's phase transition paradigm. So the first is fractional quantum Hall effect. Okay, like you have a two-dimensional quantum Hall sample, and if you measure the transverse electric conductivity, okay, there will be some fractionalized quartet. Okay, so at different fitting numbers, okay, they have the same symmetry, but there is a phase transition, so it's beyond Landau's paradigm. And so then there are also some observables or physical quantities can describe such phase. It's no longer order parameter, but like there are some non-trivial ground state degeneracy. So it's quite amazing that if you put the system onto different manifolds, okay, it has different geometry, then it will give you different ground state degeneracy. And there are some fractionalized or fractional statistics. Or fractional charge. So the excitations in this system is no longer of the boson or fermion. It's something called annual. Okay, it has non-trivial neutral statistics or self-statistics. And fractional charge is the charge of the excitation is no longer the integer multiply the e. It's some vector. Okay. Called annual. It's no longer boson or fermion, it's called annual. Okay. Oh. So annual just means the statistic phase is not +1 or -1. It can be some arbitrary, phase, or something more complicated.
What is fractional charge?
Like,
What is a charge?
so the excitations in system, it carries charge, but it's not like 3e or 4e. Like one third of something like this. Okay.
So how about activating the integer on point?
Yeah.
How do we make them with?
So integer quantum Hall effect is it's also some kind of gap quantum liquid phase, but the reason why I did not put it here is it's what we call trivial gap quantum liquid phase, trivial phase, which means there is no fractional statistics and there is no fractional charge.
Can this fractional statistics and fractional charge be measured directly from the experiment?
I think there are some early experiments like Lovelin's, or I remember they have done the experiments. And something called the second source is something called parallel spin liquid. So this kind of physics emerged from the study of high temperature superconductivity, and it was realized that different parallel spin liquids can have the same symmetry, but different number of the so-called heat conducting H modes. And the third source is 2 + 1d transaminase. Topological quantum field theory. Okay, and so this quantum field theory is it described some it described the ground state. So the Hamiltonian of the topological quantum field theory is 0. The Hamiltonian is 0, so it describes the ground state. And it turns out that the 2 + 1d transaminase TQFT is the low energy effective theory of fractional quantum Hall effect. Okay, so motivated by Professor Xiaogang Wen, such kind of gap quantum liquid fields are called topological order. So these new phases are called topological orders. Okay. All right. So now let's talk about the motivations that why such kind of physics is important. So first, So I'll talk about motivations. So the Landau phase transition theory is not studied from the first principle. Like it does not give us a rigorous definition of what is a phase or what is a phase transition. It's just a phenomenological theory. Okay, and the phase of topological orders, it's much simpler. Okay, which means that so such kind of phases are gapped. By gap, we mean so only the ground state of such phases are matters. So it's much simpler than the gapless phases. So maybe we can study the phase from the first principle. Okay, we can give a relatively rigorous definition of what is a phase, or at least what is the topological order. Okay, so actually, there have been many attempts to giving such definition, both macroscopically and microscopically. So what is it? Study. Yes. So microscopically, an equivalent class of such gapped quantum liquid phase is just a class of lattice model. Okay, right? Microscopically, it's just a lattice model. However, since the phase itself is defined in the thermodynamic limit, it's something macroscopic. So maybe we can define the phase from the macroscopic perspective. Okay, and it turns out that so it's gapped. We want to study their ground state, which means that we need to take the long wavelength limit. So like for a gap phase, like so this is spectrum and this is its gap. So the energy gap, and we only want to study the ground states, like the states below this gap. So we need to take the long wavelength limit. So we need to see it from the far away. Like so, this energy gap, this energy characteristic energy, corresponds to some length, some characteristic length, like psi is equal to 1 over delta. And so if we only care about the physics happened in the thermodynamic limit, or in a very large length scale, so if the L is much larger than this psi. So equivalently, it's just this delta goes to infinity. So which means that only the ground state survive. So this is what we mean by taking the long wavelength limit. Okay. So for gap phase, we only care about the physical observables in the non-wavelength limit and the thermodynamic limit. For the phase, this definition can it should be defined by the collection of the physical observables in the non-wavelength limit and the thermodynamic limit. Okay, and it turns out very surprisingly that if we only study these physical properties in the non-wavelength limit and thermodynamic limit, the categorical structure emerges. Observables in the non-wavelength. So it gives categorical structure. So here is some new mathematical structure called category theory emerges. Very surprisingly, that the new phase corresponds to some new mathematics. Okay, so maybe we can just use this categories. Okay, we can just classify all the categories, and it can just help us to classify all the phases or all the topological orders. And since the topological order is gapped, and so so if we can study the topological orders from the categorical perspective, it can help us define some more complex phases, like some gapless phases or some phases with symmetry. So this is the first motivation we care about topological order. The second is that so topological orders has many impacts higher energy physics. So there are many methods in topological orders and many results in topological orders. There's something like many body entanglements in topological orders, and something called string net condensation, and the bulk boundary correlation. So all these results are from topological orders, and in the high energy physics, it can be used. Okay, so it is useful in like string series and some quantum gravity and ADS CFT. So I'm not an expert on high energy physics, so I know that. It's another very interesting point, like, is that so why is such kind of ideas or concepts or results can't be used in high energy physics. So maybe if we want to answer the question, what is the bit or what is the particle, we need to answer the question, what is the space or what is time or what is elementary particle. So maybe they can't be separate, or they are just the same question. So another thing is another motivation is its impacts on pure mass. Okay, so math and physics are old friends. Like any important physical revolution is based on some mathematics, like the Newtonian mechanics based on calculus, and the Landau-Fish transition is based on group theory, and like quantum mechanics is based on linear algebra. Right? So mathematics always have many impacts on like physics, and it's the same in topological orders. Like the group theory or homotopy theory, and some higher algebra or conformal field theory helps a lot in the development of topological orders. But topological orders, in turn, give many intuitions for mathematicians to define new mathematical concepts. Okay, so it arises many problems and gives mathematicians many physical intuitions. So one thing is interesting that so in this paper we are reading gives an answer, a philosophical answer about why physics can help developing mathematics. So it's very interesting that mathematics it may have infinite numbers of degree of freedom. It's very complicated, and actually when defining mathematical concepts, we always are lack of some intuitions, global intuitions. But if the mathematics can describe some physical system or some like quantum many-body system, so we can observe this physical system and or do the experiment or just look at it. So the physical detecting is a highly non-trivial renormalization process, right? So it just like it integrates out many microscopic degree of freedom and give you some physical physical quantities. Okay. So this is the first part, and then I will give some a little bit more fresh definition of gap quantum liquid phase. Okay, so we can first give a definition from the microscopic perspective, since it's always simple to operate some very small, right? first, from the macroscopic perspective, the phase is just a equivalent class of lattice model. So here we just give a definition of the lattice model we use. So a lattice model. So it's the lattice model is a collection of the following data. So so first there are some discrete sites in the space. Okay. So these sites are called lattice sites. And then for each site, there is a so-called local Hilbert space. Okay, so for every site there is a local Hilbert space, and the total Hilbert space is just the tensor product of all these local Hilbert space. The total Hilbert space H is the tensor product of all these local Hilbert space. Okay. And the Hamiltonian of a lattice model. The Hamiltonian is something like this. So we want a Hamiltonian contains only local interaction, which means it's a sum of some local operator, which means so it only have effect on several lattice sites. Other lattice sites is just the identity operator. So it's the local interaction. It's only local interaction. Okay, and so the equivalent class of the lattice sites would be taken when the number of lattice sites goes to infinity. And so the phase we care about is called quantum gap, the quantum liquid phase. So by gap, we actually mean that when you approach to the thermodynamic limit, so when the number of lattice sites goes to infinity, there is always an energy window. So inside this energy window, there is no state. Okay, so there is always means there is no gap closing. and it's not enough. And we also require that so the number of states below this energy window or below this gap.
Sorry, can you yes, what the local interaction means? And the Hamiltonian is local.
So local interaction just means it's so it's just a sum of some local operator. So local operator means that it only affects certain the sum of local Hilbert space.
But still not what is local.
Like how local is local? Is it local on each side?
This is a very tricky question. So how do we mean by local?
Like
One of the answer is that you can consider all finite number of lattice is local. So the infinite number of lattice is non-local. Like the quantum Ising model. Okay, so the sigma I z, sigma I plus 1 z. This is local because it only acts on I and I plus 1. There is no effect on other sides. And if you have an operator like in a tensor product of I, like okay, so such operator is non-local. It's just a times of all operator on the right side of 1. Okay. So by gap, the first we mean there is always an energy window, and in which there is no energy eigenstate, and the number of states below the energy window. Doesn't change. So first it's the number is finite. And doesn't change. When taking the thermodynamic limit, approach. And the third one is that so when approaching the thermodynamic limit, so the states below the energy gap, right? So this is the gap, and when you're taking the thermodynamic limit, when you're approaching to the infinite large of the spatial size, the energy splitting of this state goes to 0, which means that they are almost degenerate in the thermodynamic dynamic limit. So energy splitting of I would say of the states. Scale close to 0. Okay, so this is what we mean by gap. And another word is liquid. Another word is quantum. By quantum, we just mean that we only care about the ground state. Okay. There is no thermal fluctuations. So by liquid, mean that from the macroscopy, so if you see the phase from far away, like the phase is unit, it's isotropic. There is no special orientation of the phase, so it behaves like a liquid. Okay. So from the phase looks uniform. So I think the word is originated from the early study of fractional quantum Hall effect. So there is a correspondence between the quantum Hall states and so-called uncompressible liquid. So I think the word liquid comes from there. So although we do not know what exactly we mean by liquid, but physicists always have some intuitions. Like we know what kind of phases are not liquid. Like liquid crystal is not a liquid. It's always have some special orientations. So it's not what we want to describe. Okay. So now we give an example of the simplest example of gap quantum liquid, which is called trivial gap quantum liquid phase. The trivial phase. It's determined by so the local Hamiltonian is the vector space, right? And there is a projector. So the local operator pi. Okay. And so its projector means that it has a unique ground state. Like psi projects to 0. Okay, and the Hamiltonian is just given by sum over this pi.
You mean projection? Trivial.
Yeah. I think maybe only psi it projects to psi, and for other states it projects to 0, right?
Do you, this is local. Yeah.
So maybe the Hamiltonian should be defined by minus sum over psi, sum over pi. It's just the tensor product of all these psi lines. Okay, so it's a trivial phase since it's just the tensor product of the ground state and on the local side. And we denote this trivial phase. So if it's in n dimension, we just denote the trivial phase. So this is called the trivial phase. And denoted by. Okay, so this n means spatial dimension is n. Okay, and so actually, so if we have two gap quantum liquid phase in n dimension, if we denote them by an and bn, okay, we can stack them together like so. This is an and this is bn. We just put them together, and there is no interaction in between. Okay, and such phase is denoted by a box tensor. Yeah. Okay. So this is the simplest way we can make a new gap quantum liquid phase from the phases we already have. And the trivial phase is the tensor unit, okay, or box tensor unit in under such box tensor. So so for any gap quantum liquid phase, we can box tensor or stacking a trivial phase, and it's still the original phase.
How exactly does a false tensor thing do?
Actually, it has a rigorous mathematical definition, but I do not want to explain here. But physically, it just means put the two layers together.
Right. How is that different from the usual
Um,
This A and B is not trivial space. This A and B means the topological form.
or some phase. Okay, so like the normal tensor product, maybe it's a tensor product of some element, some vector. But here is a tensor product of two phase.
I have a question.
Yeah.
What's the meaning of this psi I? Is it just any vector in the I universe space, or is some special vector in this universe space?
So I just want to see that it's the ground state of this local operator.
Okay, ground state.
And all this local operator commutes. So the global ground state is just a tensor product of each ground states of the local set.
So then the tensor product of all these ground states get psi. So this psi is the ground state of the system.
Yeah, this is like the ground state of the global system.
I see.
Okay. So this is a general like definition of gapped quantum liquid phase, and the topological order is a special kind of gapped quantum liquid phase. So logical order is just orders. Without symmetry. Okay. And for other gapped quantum liquid phase, like with symmetry, they can be further divided into so-called symmetry breaking phase and symmetry enriched topological order, or symmetry protected trivial phase. So gapped liquid phase. We'll just say gapped quantum liquid phase with symmetry. Can be further divided into simultaneous symmetry breaking phase.
I'm sorry, there is a question.
What does mean by topological gauge transformation? Actually, I don't know how to answer this question.
You illustrate your question again. Further.
Yeah, can you say it in more detail, like in what context do you mean by a topological gauge transformation? Or maybe we can talk it later. Like, all right. And symmetry enriched topological order, or SET, and symmetry protected as a trivial phase. Or SP. Actually, like the theory of SET and SPT, like are mainly development by the two professors at CUHK. All right.
I have a question.
Yeah.
Can you give some examples of systems without anything? I just cannot imagine anything without anything.
So let me see how to.
Maybe the symmetry, all the symmetry are local, no symmetry.
First, the definition of the topological order is gap liquid.
Yeah.
So you say liquid is something that is isotropic for unit.
Yeah.
And that means you may have something like rotation or translation.
Let's see.
This symmetries are big.
Actually, I think the symmetry is some kind of constraint, like in topological order, or what do we mean by without the symmetry, which means that the system is allowed to adding any kind of perturbations in it. But with symmetry means you can only add some symmetry allowed perturbations. Then the perturbations should commute with the symmetry operator, something like that.
So we can, I think we can break the isotopic. Actually, we can add some explanation or defect to break the system. So that is what we mean. There is no system. We can break.
We can. So without symmetry means that we can add symmetry breaking terms to the Hamiltonian.
We can add some potential energy or some defect to break the Hamiltonian symmetry. So we don't have any we don't have any local. Whether the spring and model has a symmetry, because it is in the honeycomb that is has a rotational symmetry.
So I think when you consider a lattice model, okay, like there is always the symmetry means that something commutes with the Hamiltonian, right? So actually it's something global, but when we talk about a phase without any symmetry, it means you need to see it locally, like how to say, so I would say here without symmetry is just you can add any kind of perturbation. Any kind of perturbation is allowed. But if you consider a system with symmetry, you can only add some symmetry allowed perturbation in it. Maybe I will give a better answer next time. Okay. All right. The next thing is it's called the pattern of the. So if you want to like study the physical observables from the from the microscopic level, okay, the physical observable makes some correlation functions or sorry, so if the system is gapless, okay, if the system is gapless, then the physical observables may be some correlation functions. Okay, it's non-vanishing, but for gapless system, the correlation functions are it will decay exponentially. So in the thermodynamic limit, so the correlation function is just 0. So what kind of observables are we should really care about? The main point I want to make is that although a phase is defined in the thermodynamic limit, okay, but it's still a local concept. So here local, I mean that no matter where you put the phase on, like you can put the fractional quantum Hall phase on a torus or a sphere or anything else, but as long as they have a same filling number, they are the same phase. Okay, so there may be some global observable. Okay, but maybe their Gaussian degeneracy is not the same, but such observable is from the properties of the geometry or topology of its background. It's not the intrinsic properties of the phase. Okay, so so if we want to care about the observables of the phase itself, we should not consider the topology or geometry of the background itself. We should only take a open disk of the topology or geometry. But this local doesn't mean it is not contradictory with the thermodynamic limit. So we just so we can put some phase on towers, okay, and we can also put a phase on the sphere. Okay, so they are the same phase. We mean that if we see it locally, they are same. Okay, but here locally we mean you take the local piece of the states and you just extend it to a thermodynamic limit, and we look for the observable in such local patch in the thermodynamic limit, and that will be the observable we should care about. So here we mean let's see the physical so there will be some observable called global observable. And some observable we call by Rn So such kind of observable, so global observable is something you can see when you consider the topology and geometry of the background degeneracy. Okay, but that's not the properties of the face. So what we should care about is the Rn observable. Okay, so quantum phase should be characterized by all possible Rn observable. So Rn just means we extend it to thermodynamic limit. Since locally, you see locally it's just an open disk, and we extend it to thermodynamic limit and look for the observable. Okay, so so now we talk about the observables of such gap quantum liquid phase or observables in topological orders. So since it's gapped, as I just said, there is no correlation function in the thermodynamic limit. So the observables are something called topological defects. And topological step. Okay, so we have said that topological order is some kind of liquid phase. Okay, from the macroscopic perspective, it's uniform. It's isotropic. So something can be observed is that we just break the uniform or break the like we create some defect in this inside this space, inside this liquid. So so macroscopic, we just add some local perturbation or dislocation or some local terms into the Hamiltonian, and it may break the uniform of the phase. So so for example, we can add some maybe some local term. So omega is the local region, like the original phase. If you look at the phase from the long wavelength limit, it's uniform, right? Just something like this. And after when we add the local perturbation, or we add some dislocation, like so maybe the original lattice size is something like this, and we just change it into something like this. Okay, so then from the long wavelength limit, if we just see this space again, there is something different. There's some defect in this space. Okay, so this is the observable in topological order. So if we add some local term, or if we introduce some this dislocation, local dislocation. So for example, in this case, like we may just change something here. Okay, so in the region we add perturbation, it will trap some defect or trap some quasi particle. Okay, so if this quasi-particle or this defect can be seen in the long wavelength limit, so it's the observable we want to it's the observable we want. So what do we mean by we can't see the this quasi-particle or this location in long wavelength limit? So when we approach the thermodynamic limit or long wavelength limit, the microscopic degree of freedom is no longer important. Like we can add any kind of local operator on this state. Okay, so like if we after we add this local perturbation, the ground state, like the original ground state is psi. Okay, and if we add this perturbation, it will be something like psi omega. Okay, so at omega there is something different. So if we can see this omega in the thermodynamic limit, that means that we can add any kind of local perturbation, and this perturbation will not annihilate this quasi-particle. So if it's not annihilate this quasi-particle, this defect this defect can be seen in the thermodynamic limit. Okay, so a topological defect is just a equivalent class. Like for example, we say X is a topological defect, and it's defined by all kind of states of this form and scope. Okay, and so if there is some local operator such that when it's acting on the new ground state and it becomes the original trivial state, it means that this defect cannot be seen in the thermodynamic limit. Okay, so the trivial defect is just defined as the original ground state. Okay, so okay. So the topological defect is the observable in the topological order. Is there any question?
Here, the observable is different from the observable in the context of the quantum mechanics. Because in the quantum mechanics, we say an observable is an operator.
Yeah. So here, observable just means we can really see it's different from its nearby. It's some defect, or it's something something we can see in the long wavelength.
What do you mean? Can see, like you see, you say that there is a defect or there is not.
It just means it's different from the nearby. Okay, so like after you add some local term, or if you introduce some dislocation, so if you see the phase from the long wavelength limiter, it will be different from the nearby. So here is still isotropic. Here is still like uniform. Oh, sorry. Okay, here are still liquid, but this is different from the phase nearby, so we can see it, and we can see this location is different. So I think another example maybe better, like you have icing chain. Okay. So this is an icing chain, and like the ground state is like all the spins pointing up. Okay, so if there is just one spin is flipped, and you see such state in the long wavelength limit, we cannot see such spin flip. But if we just flip all the spin on the right hand side, like so if we see such state in the long wavelength limit, so we know there is some domain wall, some defect in space. So here we mean the observable.
But here you do not change modify the component.
You can add some term such that such kind of state is a ground state. Yeah. So next time we will talk about some, we'll give an example lattice model. So all this definition can be okay, and so this is a topological defect, and the collection of topological defects is defined as a topological skeleton. Topological skeleton. The collection of all topological defects. And such a topological skeleton is not just a set. Okay, although it's a set of all topological skeleton, but it has like it has some algebraic structure. So, for example, you have a two-dimensional topological order, and so here is some codimension one or just a one-dimensional topological defect in this space. Here is another topological defect. We'll call it so it's okay. There are two topological defects, and if we again see it far away, see it in the thermal in the long wavelength limit, it's just one defect. Okay, and this defect is called M box tensor C. Okay, so there is a algebraic structure in this topological skeleton. And also, if you have some point defect, and you see it in the long wavelength limit, the 2 point-like defect will fuse to 1 defect. I think it's better. So it's M1, and there is a point-like defect, and M2. This is X. This is Y, and this is M3. So this is M1, M2, and M3. So in the long wavelength limit, the 2 point-like defects will just fuse together, and what you can see is M1 and something like X of M, Y, and M3. This is what you can see. So all the skeletons in the same dimension can fuse together and become another topological defect in the same dimension. So actually, the topological skeleton is naturally a higher category. So it also forms a category. Okay, one last thing I want to say is anomalous and anomalous grid. So we started the discussion about the gap quantum liquid phase by assuming that there is a lattice model kind to realize it. But that is not always the case. Like there are some quantum phases cannot be realized by a lattice model. Okay, so an n-dimensional quantum phase is called anomaly. Called anomaly field. If it can be realized. By that. And so, and it's called anomalous. If not. But actually, there is a physical theorem that if ND quantum phase is anomalous, okay, so if it cannot be realized by an n-dimensional lattice model, here I want by this is important, by an n-dimensional lattice model. So so it's anomaly free if it can be realized by the lattice model in the same dimension. Okay. And it's anomalous if it can be realized by that model in the same dimension. So if a quantum phase is anomalous, okay, if it cannot be realized by a lattice model in the same dimension, then there is a physical theorem that it then can be realized as a boundary of a one-dimensional higher lattice model. So n-dimensional anomalous quantum phase can be realized by boundary of a one-dimensional higher lattice. So if an n-dimensional anomalous quantum phase, okay, so it always can find a bulk, right, which is a one-dimensional higher lattice model. And such lattice model or such bulk is, it may not be unique. Like there can be, or there may be more than one-dimensional higher lattice model can boundary can realize such anomalous quantum phase. But for topological order, so if AN is a n-dimensional anomalous topological order, and there is a unique bulk. Here, unique, we actually mean there can be more than one lattice model can post-boundary can realize it, but they are equivalent. Okay, I define some equivalence of such bulk. So up to this equivalence is unique. There is a unique bulk. So. And such bulk is just denoted by bulk of AN. Okay, and this is also called the gravitational anomaly of AN. Or So since this bulk is n+1 dimensional lattice model, so if we take the bulk again, it's trivial. Like the bulk is already realized by a lattice model, so it's anomaly free. Anomaly free just means that the bulk of it is trivial. It's just nothing. So it's a trivial case. Or
Do you have an example about the topological order
cannot
be realized?
Yeah, fractional. I think fractional quantum Hall is like that.
How about the boundary theory of the Fourier code? It is roughly two different categories.
Yeah.
Can it be realized by 1D lattice model?
I think since it has a non-trivial bulk, right? So it cannot be realized by a one-dimensional lattice model.
Do we have the non-trivial one-dimensional topological order?
Actually, I think it's always it has been proved that there is no one-dimensional topological order, but there can be like symmetry enriched topological order.
So we already have an example.
Yeah, I think it has been proved just by Gudong. I remember there are some articles that have proved this. Okay, this is almost done. So the last thing is yeah. So this unique bulk theorem is proved for gapped case. Okay, so if it's a gapped, anomalous gapped quantum vector case, the unique bulk theorem is proved. But physicists believe that for gapless case, it's also true. So we have not proved that, but we believe that it's true.
So this bulk is in general the functions of the frequency.
Yeah.
So what is the relation with the gravity?
I know some examples like
I heard that in quantum theory there is something called gravitational anomaly. I don't know whether that.
I think here gravitational anomaly means that have you ever heard that if the chiral central charge is not zero and it cannot be realized by a lattice model. And such chiral central charge just emerges when you do diffeomorphism of space-time. If there is a diffeomorphism like transformation, so it will give some term like C minus C bar in two-dimensional, like common field theory will give something like C minus C bar. So like we suppose that a diffeomorphism transformation, like a quantum theory should be invariant under some diffeomorphism transformation, but actually it's not. And if C minus C bar, so this is an anomaly term. after you do the transformation. And if this is not zero, it cannot be realized by a lattice model. So I think the gravitational just means some kind of like the diffeomorphism transformation. So that's why it's called gravitational. Yeah, so one last thing is that so if an is anomaly free, then if we take the bulk of it will just be the one-dimensional higher trivial space or just vacuum. I think so any questions?
There's oh yeah, you mentioned that it's up to some it comes with transformation.
It's actually some categorical equivalence called Morita equivalence, I think, right? So I do not know how to.
That thing is also topological. Topological phase, so it is up to the phase equivalence of the phase. And the E8 phase, since it has 8 single charge, so it cannot be distinguished by the trivial center. So if we can stack any member of the E8 state phase onto that block, up to such E8, we can fix it. This is the phase.
So it just means if you're stacking such deep phase,
Yeah,
and
it does not,
so it's just
we can stack any times of E8, and it still gives the same boundary.
Isn't the trivial phase also the same? Like if you stack trivial phases.
This E8 phase is not trivial. It does not have any excitation, but it has non-zero central charge, so it is not trivial. It has boundary flux, but it do not have the bulk anion excitation.
Also, is so you said for any anomalous quantum phase, you can realize it on a one-dimensional higher, the boundary of the one higher. That is one. But like, how exactly does the boundary differ from the lattice model? Because you see, the boundary of a one-dimensional higher lattice model means that the boundary itself is n-dimensional. And how does the boundary differ from the lattice model? What is the crucial difference between the boundary of the lattice model and the lattice model?
such boundary, so it cannot exist without a bulk. Like the boundary actually just means so you have like for example two-dimensional. You have a two-dimensional lattice model. And when you take the boundary, okay, you always need to like involve some bulk degree for the freedom nearby.
But if I have a circle and I take the boundary of the circle, this is stay in line. One I can have a this line without the circle.
So when we say boundary here, we cannot mean the geometric boundary. It is some physical boundary. It must have some physics can occur here, so we must include some bulk. Just like the transimus, the quantum Hall effect, it has a non-trivial H mode. The current can flow along the boundary.
But if it's just no bulk, so
But if
that's
you
no
have
touch.
bulk, we do not have that. So, 下次要讲。
Oh, all right.
下次。
So next time we'll just introduce a concrete lattice model called Topological model, and we will analyze the topological defects and like the ground state degeneracy of this lattice model and how the categorical structure emerges from the topological model. So that will be the content of next time. All right. So any other questions online? Yeah, if not, okay, I think. So so maybe I will answer the topological gauge transformation question next time. So you're free to go.
Kind of like any intuitive idea or like why can't you fuse defects together and find this really disappear?
It can be like it's just like the positive particle and its anti-particle. So the particle and its anti-particle, if you see it itself, it's